Okay, in this video I'm going to do an example of synchronous TDM multiplexing. And in this example we're going to combine 12 input signals, each with a data rate of 2 megabits per second, and we're going to construct these frames using byte-wise interleaving and no framing bits. Okay? And in part A they want us to draw a picture of the situation. And so I'll draw inputs 1 and 2 and ... down to input 12 into a multiplexer, and then draw the output. And now I'm going to draw the output frame, and I'm going to use byte-wise interleaving, so I'm going to have a byte from source number 1, a byte from source number 2, etc., and finally a byte from source number 12 in my frame. When we do byte-wise interleaving, we're going to set little n equal to 8. Little n is the number of bits per stream in the frame. And when we do byte-wise interleaving, we're going to set little n equal to 8 because in one frame we're going to take 8 bits from each source. Okay, so little n is 8 here. Big N is the number of input streams, and so big N is 12 in this case because we have 12 input signals. Finally, we can calculate the size of the output frame, and I kind of like to do it right here on the picture. It's the number of bytes, or it's the number of bits per frame per stream times the number of streams. And this is the case where we have no framing bits. And so this is equal to little n times big N, or 8 times 12, or 96 bits. Okay, it's 12 bytes. If we want to calculate the output frame rate, we can do that by using this equation, which says that the output frame rate, RF, is equal to the bit rate of one of the input signals, R1, divided by little n. And here we have R1 is equal to 2 megabits per second. Those are the 12 input signals, each having a data rate of 2 megabits per second. So that's R1, and so our frame, using that equation, is R1 over n, which is now 2 megabits per second divided by 8, or 1/4 of a megabit per second, or 0.25 megabit per second, or 250. Now this, I'm writing a little bit fast here, is mega frames per second now. Right? Right. I divided bits per second by bits per frame, and I get frames per second. And 0.25 mega is 250 kiloframes per second. Okay? If we want, we can calculate the output frame period, which is T frame, which is 1 over R frame, which is 1 over the 0.25 e to the 6th from the mega, and this is 4 e to the minus 6th seconds, or 4 microseconds. The output data rate is what we're calling R tot in our equations, and we can see that R tot is equal to the number of bits per frame times the frame rate. Okay, and the units work out. Frame rate is frames per second. The number of bits per frame is bit per frame. And the frames cancel out and we get bits per second. So the units on this equation work right out. So R tot is RF NF. And we can plug in NF is 96 and RF is 250.25 mega, 0.25 e to the 6th times NF is 96. 1/4 of 96 is, I believe, 24. Yeah, 24, 48, 96. So 24e to the 6th, or 24 megabits per second. Watch out now. We can simply take our tote equal to the number of input streams times the data rate of one of them. Because there's no framing bits, we just 12 signals times 2 megabits apiece is 12 times 2, or 24 megabits per second. So calculating our tote this way actually turns into a nice double check on our total bit rate. But when you have no framing bytes, or no framing bits, you simply say that the total bit rate, our tote, is the sum of the bit rates coming in to the multiplexer. Okay? Finally, calculate the percent of the frame that is data bits from input sources. Well, when we have no framing bits, they're all data bits, and so we have a 100%. If we have a framing bit, then we can figure out what percentage of the bits in the frame are actually data bits. But here, with no framing bits, we have 100% data bits in our frame. Okay, hope this helps. Here's an example on synchronous TDM multiplexing.